Hey guys, welcome to eMath. Today we are going to look at a very interesting integral problems which actually involve the concept of infinite series. Alright? So the problem is you integrate with respect to x of 1 over x plus 1 times x plus 2 times x plus 3 times x plus 4 blah 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 until x plus n. Alright? So yeah, that's the problem. So the first thing that came to your mind when you look at this integral is maybe a factorial, isn't it? So let's try to write it in terms of factorial. Okay, so it will be x plus n factorial. I mean the one at the bottom. Okay, let me write it like this. Okay, 1 over x plus n factorial. Then because you need to get rid of all the terms in front of x, right? All the terms in before x, so you divide by x minus 1 factorial. Yeah, fair enough. And if you flip it, maybe it is x minus 1 factorial over x plus n factorial, right? Does it make it easier to integrate like this? Maybe yes, maybe not, but I don't think I will do it today, right? So what I want to do today is actually we try to observe the pattern of this expression here, and we write it in terms of an infinite sums. Then we try to find the integral of that infinite sums. Okay, so actually if you look at it, it is x then x plus 1, 2, 3, 4, 5, 6 to n. So when n equals to 0, it will just be 1 over x, right? And do we know how to integrate 1 over x? Yes, right? 1 over x dx is just the natural log of x, and maybe if you like, you just put a modulus of it, then plus c, right? Then what about when n equals to 1? Okay, it will be 1 over x plus 1. Do we know how to integrate this? Yes, but before that, we need to do one more step, which is the partial fraction decomposition. Let me just do it real quick. Okay, the PFD. So in order to decompose this into a partial fraction, we first let it be. Okay, we have two distinct linear factors, and by the rules of partial fraction decomposition, the degree of the numerator is always 1 smaller than the degree of the denominator. And in this case, because the denominator are linear factors, which means the numerator are all constant. Okay, so in order to compare two of them, we need to have a common denominator. Okay, so I just go ahead and cross multiply bx over x plus 1. And now we can compare these two numerator. Okay, 1 equals to ax plus 1 plus bx. Okay, let me adjust the mic. Okay, cool. So because this is something that we let something be something, so it has to be true for all the values of x. It is actually an identity. Okay, so we can sub in any values of x into the identity, and it will result to be a true equation, right? So when your x equals to 0, yeah, I don't know which method you prefer, but in this case, I will just do the cover-up method, right? Of course, you can do the algebra. You can solve it algebraically by compare the coefficient of x, all right? So when x equals to 0, yeah, obviously this will just be 0, and this will be 0 plus 1. So 1 equals to a times 1, a will be equals to 1. Okay. Then when your x is negative 1, okay, because I want to do the cover-up method, when we let x be negative 1, this will be 0, right? And this will be negative 1. Negative 1 times b is negative b. So b will be negative 1, right? Then we just write it back. We will have 1 over x minus 1 over x plus 1. And do we know how to integrate this? Yeah, obviously we can, right? But can we see the pattern from this? I don't think so, right? So we have to continue and open up more terms. Okay, let me remove this PFD. So when n equals to 0, 1, when n equals to 2, x plus 1, x plus 2. So again, we need to decompose it. We need to perform a PFD to make it into partial fraction. So yeah, again, I will do the cover up method. So I will just directly do it. I hope you can understand, and make sure you write all the steps during your exam. Yeah, x plus 2 plus c x, then we have one more factor, x plus 1. So I will just do the cover up method. Okay, when x is 0, we cover up the one with x factor. Okay, this will be 0, this will be 0. And 0 plus 1 is 1, 0 plus 2 is 2. 1 times 2 is 2. So a equals to half. Stop. Okay. Then next, okay, let me erase this, erase that. Okay. So when x equals to negative 1, okay, I want to cover up this and that. Okay. Negative 1. Negative 1 plus 2 is a positive 1. And together it is actually a negative 1. So b will be negative 1. Right? Then next, when your x is negative 2, okay, this time, okay, let me erase this, that. This times, the one with x plus 2 will be 0. This will be 0. Then negative 2 plus 1 is a negative 1. Together, they are positive 2. Therefore, c will be positive half. Okay, positive half. Then we just write it back. 1 over 2x minus 1 over x plus 1, then plus 1 over 2 x plus 2. Okay, this is 1 over 2 times x plus 2. Right? So I think you can start to see the pattern already. So first of all, if you notice, it is actually positive, negative, positive, negative, right? So I think this is actually an alternating series on top. Agree? And for the denominator, we have x, then x plus 1, x plus 2. So maybe it's some kind of factorial, right? Yeah, I think so. And we still can't see the pattern, so maybe we just try to open up one more, and hopefully we can see the pattern by then, because we can't go and open up forever, isn't it, to end. So hopefully we can get the pattern by the next one. Okay, the next one, when n equals to 0, 1, 2, 3 plus 1 x plus 2 x plus 3. Again, we do the PFD. So it will be 1 equals to a x plus 1, x plus 2, x plus 3 plus b times x plus 2, x plus 3, then plus c times x plus 1, x plus 3 plus d, x plus 1, x plus 2. And we do the cover up method. When x is 0, we cover up b, c, and d. And this will be 1 times 2 times 3, which is a 6, right? Okay, so a will be 1 over 6, right? So when x is negative 1, okay, x is negative 1, we cover up a, c, and d. Okay, cover up this, that, and that. And maybe I shouldn't cross it so that I don't have to erase later. So this will just be negative 1, this will be a positive 1, this will be a positive 2. Together they are negative 2, and therefore it should be a negative half for b. Okay. Next, when x equals to negative 2, okay, I cover up a, b, and d this time. This will be negative 2. Negative 2 plus 1 is a negative 1. Negative 2 plus 3 is a positive 1. And wait, negative 2 plus 1, negative 1. Yeah. So together they are a positive 2. Therefore, C is positive 2, half. Positive half. Okay, positive half. Last but not least, when, okay, this will be a plus, okay. So when x is negative 3, I'll cover up A, B, and C. This will be negative 3, negative 2, and this will be negative 1. Together there should be a negative 6. So D will be negative 1 over 6. Just like that. Then just put it back, and yeah, I think the pattern is quite clear already. 2x plus 1 plus 1 over 2x plus 2 minus 1 over 6x plus 3. Very nice. And let me just get rid of this. We don't need it anymore. Delete. Okay. Okay, let me remind you that our goal is to write this in terms of infinite sums. Then we go and integrate the sums. Okay, so from the pattern that we can observe here, now actually we haven't drawn our conclusion, but yeah, it should be infinite sums from k equals to 0 maybe, or 1, I don't know, to n, right? Okay, if we let k to start from 0, and we know that it is an alternating series, as you can see, the numerator are just positive 1, negative 1, positive 1, negative 1, right? So we'll just put a negative 1 to the k on top. Why? Because we start from k equals to 0. Means the first one will be negative 1 to k, negative 1 to the 0, which is positive 1. Just like what we have here, right? You see our first term, okay, let me write it down. Our first term is always positive, and the second one will be negative, third one will be positive, etc, etc. And what do we have next? Okay, so if you have a look at it, okay, you have a look at this and that, x, then x plus 1, that. Just like what we said earlier, it should be a factorial. And obviously, it is a x plus k factorial. Okay, it is a x plus k factorial. And because just now we let k to start from 0, so it perfectly fits what we need here. Because you see the first term is just x, so x plus 0 factorial is just x factorial. Okay. Then here's the interesting part. Okay, let me highlight for you. It's the constant in front of that factorial. But from what we can see here, is actually symmetrical, isn't it? See, you have 6, 6, then 2, 2. And for this is a 2, 2, and a 1. And for this one, just 1, and first one we only have 1 term. So the problem is, how do we compute this constant in front of that x plus k factorial? So because it is symmetrical, so we can maybe write the hypothesis that maybe it is a product of two numbers, okay, the product of two numbers, where one is getting bigger and bigger, another one is getting smaller and smaller. Okay, but I don't know how true is that. And another thing with that we have to take note is, we need to express this constant in terms of k and n, right? We can't write it in terms of x because it is a constant. We can't let it be a variable. So Let me just write it down for you. This is what happens when n equals to 0, n equals to 1, n equals to 2, n equals to 3. Right? Then we focus on n equals to 3 because that's the one that we have the most information to draw our conclusion. This will be k equals to 0, k equals to 1, k equals to 2, k equals to 3. Okay. How do we get 6 out of 3 and 0? And we know that it is a product of two numbers. 3 times 0? I don't think so, right? 3 plus 3 times 0 is still 0. But the thing that we know is, luckily we know that 6 is actually 3 factorial. Okay, so we already got a 6. Okay, let me write it down. 3 factorial is equals to 6. Okay, so now we need to multiply it with a 1 so that it is still a 6. And luckily we have a 0, and we know that 0 factorial is equals to 1. Just go ahead and multiply it together. It is 1 times 6, so it is 6. Very nice. And I hope this works for all the constant at the back. Okay. For the second one, we need to make a 2 out of 3 and 1. And obviously, 3 minus 1 is a 2, right? And 1 factorial is 1, right? 1 times 3, 2. 1 times 2, okay, so we have a 1 times 2, which is a 2. But we need to maintain the pattern. And for the first one is a product of 2 factorial. The second one should be a product of 2 factorials, isn't it? And luckily, 2 factorials is equals to 2. So just go ahead and put a factorial here. And I hope this is true for all of them. For the third one, we need to make a 2 out of 3 and 2. Okay, we know that 2 factorial is 2, right? Just go ahead and write down it and multiply it with a 1, which is 3 minus 2, right? So it will be 2 times 1, which is still a 2. And again, we need to make sure the pattern is consistent. And luckily, 1 factorial is equals to 1. Just go ahead and put a factorial here. So far, it's true for all 3 of them. What about the last one? We need to make a 6 out of 3 and 3. And yeah, obviously we can't do 3 plus 3 because we need to maintain the factorial pattern, isn't it? So, again, 3 factorial is equals to 6. Just go ahead and multiply with 1. How do you get 1? It's either 0 factorial or 1 factorial. And we can do is 3 minus 3 factorial, which is 3 factorial times 0 factorial, which is 6 times 1, which is 6. Okay? So from here, we can obviously see the pattern of it. It is actually k factorial times n minus k. K factorial times n minus k factorial. And if you go ahead and check for n equals to 2, n equals to 1, n equals to 0, or even n equals to 4, 5, 6, 7, 8, 9, 10, if you have the time to open it up, you should be able to get the same pattern as well. So this will just be k factorial n minus k factorial. Very nice. And this is our integrand. What we have to do is to integrate this. Okay, so let me write it down again. I will just write it here. Okay, you integrate the summation k equals to 0 to n negative 1 k. Again, it is an alternating series. Okay, then x plus k factorial. I don't think it has a factorial here. Okay, sorry about that. It is we don't have a factorial here. Okay, the factorial is here. Okay, k factorial n minus k factorial. Okay, let me write it in black. K factorial n minus k factorial dx. Okay, how do we integrate this? It looks scary, isn't it? But don't worry, because we are integrating with respect to x, which means all the n, all the k, they are all constant. Right? But take a note of it. We can't just take out the sigma notation and throw it before the outside, because we still have a k here, and you know what I mean? The k is inside the sigma notation, so we just can't take the whole thing out. But we still can integrate this, isn't it? So if we integrate 1 over x plus k dx, and remember, k is a constant. This will just be the natural log of x plus k, and if you like, you put the modulus, then plus c. Okay, it actually doesn't matter because k is always positive, right? So, but your x can be negative, so you better put a modulus for it. Okay. So last but not least, this integral will just be the summation of k equals to 0 to n of negative 1k k factorial n minus k factorial times the natural log ln absolute value of x plus k. Okay, you bracket the whole thing plus c, and that's it. Okay, so that's all for today. I hope you liked my video. See you guys in the next video.